Good afternoon, everyone. Welcome to the CI's session. We have received a lot of abstracts for this session, so we will take more than 2 hours, and then you will have to shorten your lunch break. Just a joke, sorry. Since we have received indeed 16 abstracts, we decided to split the presentation in 4 sections, in 4 topics: CI's drift, CI's type, multi-sensor synergy, and in situ campaigns. And the first 2 I will present, and the multi-sensor synergy and in situ will be presented by Malin. And I'm honored to present my co-chairs, Robert Schufman, who is sitting here, and Wolfgang Dirking and Ronald Kwok, who are hopefully online. So I will continue with the ice drift topic. And when I talk about, or when anyone is talking about CI's drift, it's always deformation implied. So we can just use SID as the acronym for CI's drift and deformation. There are many slides, but like it was not enough, I also took some slides from the recent IACVGDA conference and even some unpublished work because I think it's relevant. And I structured my presentation a little bit different. I was following the guidelines very strictly, so I will present key objectives that I summarized from all the presentations. I will show some of the innovations, the key slides from the presentations we received. And then I will also show the summarized remaining knowledge gaps and the outlook and the recommendations. And first I will go through CI's drift and then CI's type with the same outlook, with the same structure. So the key objectives of the CI's drift from SAR. First, it is to develop a CI's drift algorithm. And unlike all previous presentations, in CI's, the SAR is used much more empirically and less theoretically. So all the algorithms are, in a way, image processing algorithms rather than signal processing algorithms. And for ice drift in particular, all the algorithms deal with 2 sequential SAR images and ground range, and then they do some sort of pattern matching to find where the ice has moved. And so to develop an algorithm is still an objective for some of the presentations that I will show. And then, of course, to validate this algorithm and to tune the parameters of this algorithm to have a better performance. And then what's more maybe interesting, what are the applications of CI's drift algorithms? And these are the operational ice monitoring. And if it is automatic ice drift, then the resolution should be higher than on the manual ice charts. Then it is production of a longer time series of ice drift for more climate research. Then alignment of multi-frequency SAR imagery for SAR for ice type classification on both, and alignment of multi-temporal C-band images also for a better ice type classification. So in these 2, ice drift is used as pre-processing for ice type classification. And then calibration and validation of CI's models, testing applicability of future missions, and also assimilation into CI's models. And please interrupt if you have any questions, or authors, if you think I'm wrongly interpreting your results, please also stop me. So now I'll go through a few of the slides that we have received. The first work I would like to present is from Xiaoming Li. It is a typical example of CI's drift algorithm. It consists of 2 steps. The first step is feature tracking. It is quite fast. It is using computer vision algorithms like ORB or SIFT, but the results are very inhomogeneous, and this is then used as the input for the pattern matching, which is more consistent. It can produce uniform field of ice drift vectors. And then this drift product is validated against buoys, in that case mosaic buoys from the mosaic expedition, and you can see collocation of drift vectors derived from SAR images and from the drifters, mosaic drifters. And the errors are quite low, with just a few centimeters, and the errors are higher for summer, and that's typical for other applications as well. Another result of this work is that we can actually adjust the temporal interval between the sequential images to improve the quality, because the longer is the interval, the more processes are happening between the images, like deformation, melting, freezing, and so on. And in winter, up to 20 hours is fine, but in summer, it should be as low as 12 or 16 hours between the images to maintain a homogeneous accuracy of the ice drift algorithm. So in this work, there are some suggestions for appropriate temporal intervals. Another work is by Juha Karvonen, and it's another example of an algorithm. And here also two images on the output, on the input, sorry, and then SAR pre-processing, and then a two-step ice drift retrieval. First is again feature tracking using ORB, and then pattern matching using optical flow, and then some post-processing and sea ice drift. And this is an example of ice drift from the Baltic Sea. And this is a part of Copernicus Marine Services. Here you can see vectors, and this is the magnitude. And it's interesting to see some fast ice and land fast ice and fast moving ice that can be distinguished on this ice drift product. It's accuracy. Okay, that's the accuracy of the data. Okay, thank you, Juha. Yes, so the vectors are here showing ice drift velocity, and this is the accuracy of ice drift. Another example, this is actually from ICVG DA conference that was a few weeks ago in Oslo. Presented by Sean Helfrich from NOAA. They have also developed an algorithm for ice drift, and this is an example of ice drift vectors, which are probably somewhat strangely projected because they look like ice drifts towards the North Pole, mostly. But it is just an example that these algorithms are being developed all over the world. And yet another example now from Canada. They have a slightly different approach. They don't have a regular grid of vectors. They have irregular mesh of initial points, and then they derive ice drift at quite high resolution. And then they also compute deformation in each scene, and it can characterize linear kinematic features in the entire Arctic on different temporal and spatial resolutions. So these are just examples of different algorithms being developed and different products being created using these algorithms. And now come applications. So first application is alignment of different images. This work is by Denis Demchev here. So they had a master image from L band, and then they can derive drift from a pair of L and C band. And then they can morph the initial image to match the time of the C image. And then these aligned images can be now used together for sea ice type classification. Another example of using sea ice deformation is assimilation into models. So here we have total deformation computed from ice drift, and this is a product of CMEMS produced by DTU. And then we can take this deformation product and assimilate into a model, CIS model called Nexim. And here is an example of impact of this assimilation. So here we have a forecasted total deformation without data assimilation. And here we have a forecast with assimilation. So these observations were on 15 January, and these are observations on 16 and 17, so 1 and 2 days after assimilation. And then we can see that the observations match with the forecast better than with forecast without data assimilation. So SAR-derived ice drift can improve forecast of CIS deformation forecasts. What's also interesting is that when we have data on CIS deformation with gaps because of not optimal acquisition by Sentinel, we can still improve the forecast outside of the data coverage. So on this map, the gray color shows the coverage by the observations that were assimilated, and the colored field shows the observations on the next day. And there is some area where we didn't have observations to assimilate, but we had observations to validate the model. And here is the forecast with data assimilation, and it shows that the model is capable of extrapolating the assimilated deformation in a realistic manner, so that the forecasted deformation fields are correct even outside the area of assimilation. And then a final example, which is actually linking to what Paco was showing in his presentation. It is also ice drift, but it is also relevant for Doppler. Here we used ice drift for trying to evaluate if we can use harmony in future. And in this work, we used Nexim with the different parameterizations, and we run a forecast with different parameters and predicted ice drift and ice deformation. So in the first column, you can see slightly different parameters in the rheology and which impact quite a lot the deformation field. And then we used the end-to-end simulator to simulate the Doppler shift signal that would have been seen from harmony, and inverted that back to ice drift and back to ice deformation. So in these two columns, you can see inversion, and this is the preliminary version of the inversion algorithm, and this is a little bit better. And you can see that there is still a lot of noise in the ice drift from harmony because the speeds are very low. And there is very strong thermal noise in the Doppler signal over sea ice at the level of the signal. But after cleaning up, we can recognize some of the main features that are also present on the initial run. And unfortunately, the statistical difference between these two fields is not very large. So harmony signal can be used, for example, for assimilation, but maybe not for tuning of the model parameters. So what are the challenges and knowledge gaps? Here is the summary for ice drift algorithms. First of all, it's a high thermal or speckle noise. And then the question is how to suppress this noise, or how does it affect the ice drift, and what to do with this noise. Another challenge is that under some conditions, like in summer or in the MEES, the contrast between ice and water, or between features on the ice, is too low. So a good maximum cross correlation or other pattern matching is not possible. So how to improve the informativeness of SAR images, and how to efficiently use both cross and copolarizations simultaneously for improving this image processing. Another challenge is that the surface of ice can be changing rapidly. It's either due to melting or due to a very small scale deformation, like flow rotation and so on. So how to adapt time delta between images and what is the optimal time delta? And maybe we shall go to really the highest possible resolution to derive trajectories. And when we work with different frequencies, there are inherently different patterns in C and L band imagery. So MCC doesn't work always very well, and the alignment of the L and C band images need to be somehow evaluated with a new metric. And then the challenges for applications are the following. So for the alignment algorithms, the small scale changes complicate morphing because when you have a rotation, the morphed image looks very smooth and it is not very efficient for further ice type classification. Another problem is that there is no ice drift product, Lagrangian ice drift product, similar to what we have used previously, the famous RGPS ice drift product, which has trajectories derived from RadarSat-2 that were spanning the whole season. And now we are working mostly with snapshots, which are probably good for operational, but not for in-depth analysis of sea ice. So this needs to be improved. Another challenge is that we now have a lot of data, and we have to optimize our algorithm to make it parallel, to use GPU optimizations and so on. And also, we need more resources for processing of this data and for optimizing algorithms. And with the loss of Sentinel-1B and not clear plans with Sentinel-1C, the data coverage is reduced. So we would like to use RCM, but where to get that and how to adapt algorithms, that all require some work. Outlook, based on these presentations, one of the interesting things is to use artificial intelligence or machine learning for ice drift retrieval. And it has not been done previously. So this is probably a very interesting avenue since AI develops so fast. Then some new methods for post-processing of ice drift vectors need to be developed for discarding wrong vectors or optimizing the drift fields. Improvement of parameters of the algorithms, like intervals between images, is needed, and optimization of the algorithms for parallel processing, and also allocation more resources for processing. For input data, the recommendation is to launch an operational L-band SAR constellation to complement the C-band SAR constellation. And there should be better products, like with a higher temporal resolution. And there is a recommendation to develop a high resolution and long time ice drift dataset, Lagrangian ice drift dataset. And also outlook and recommendations for the applications of ice drift. One potential application can be to derive sea ice thickness by combining sea ice drift and thermodynamics. Another recommendation is to move towards integrated system, because so far people are working mostly with observations or with a simulation or with models, but it's good to start combining that together so that observational algorithms can be adapted to what the models need. And then some suggestions for using a new metric for evaluating the alignment were given. And suggestions that the sea ice drift algorithms need to be tested under different environmental conditions, and sea ice drift and alignment algorithms. It would be nice to reduce noises harmony data I don't know how, but maybe we can task the engineers and yeah, eventually put some higher requirements for the Sentinel next generation, for example. It can also be interesting to use Harmony for detection of marginalized zone where the ice becomes more mobile despite very high concentration, unlike unbroken ice, which is less mobile. Yes, the ice drift can be used for estimating a practical predictability of sea ice deformation or linear kinematic features. So far, it has been done mostly theoretically, or inherent predictability was estimated, but practical how we can use that also should be also evaluated. And finally, we need to develop new metrics for model calibration and validation using sea ice deformation data. The LKF metrics and the general spatial and temporal scaling analysis that was performed is probably not sufficient anymore. So that was it for ice drift, and I would like to make a little commercial pause. We are involved in the Cryosphere Virtual Laboratory project at the Nansen Center that is building a platform where you can search for data and process it online without downloading. I have a few leaflets for you, so you can contact me. And we offer several workflows like online data search and 3D visualization, and online data search, and then download of the data and software to your computer if you want, or online data search and online processing, or even batch processing. And here is just an example of a recent SAR image and change detection over long-year Buin in a 3D viewer that we were building in this visualization platform. Any questions for ice drift? Ben?
So in the RGPS, the Lagrangian tracking was heavily manipulated, heavily contributed by a person who actually filled in the vertices as the time went along, because not everything could be tracked. So a person manually went into the images, the pairs of images, and reset the vertices of each grid point.
That's new to me. I couldn't find that in the report.
It was a guy at JPL and another person at the University of Alaska. I mean, they did this, unbelievable work. It's so tedious, and that's why we're not doing it with NISAR, for example. So you got to think about that for Lagrangian is how, and are there? I mean, you mentioned using machine learning. So is there any machine learning that will project? I mean, what I know is that mostly it's feature identification, basically. But in order to use machine learning for ice motion, for example, where you have lots of deformation, lots of things going on, you'd have to project. You'd have to go search for these features. And I'm not sure there's the machine learning capabilities capable of that. That's an interesting question.
It's very interesting. I made a brief search online, and there is, for example, FlowNet or FlowNet 2.0. And actually, if you search for that, you will find even large archive of data for motion detection with deep learning. And there is kind of a benchmark and a large amount of different deep learning methods for detection. And then they're using 3D fields that are used to generate some figures moving and some background motion. So it works well on for automotive applications. Probably it would work also for ice drift.
Interesting. All right, thanks.
Thank you. Katerina?
And just to comment about artificial intelligence or machine learning, so you're referring just to, I don't know, to assure people that I guess in future we're not going to replace with any algorithms like a manual and tedious work and expertise, but rather remove robots out of a human and actually help with the tedious work. So yeah, I think it should be encouraging to try to use modern technologies, which is currently, available open source. I was also looking on the recommendations that were put, and I was wondering if there is also something in the ESA message when it's referring to the uncertainties in the available data sets. Because as far as I understood, the error estimate in the uncertainties, they're not really available together with the data sets and kind of missing. There are standard metrics of uncertainties, but they may be not well represented for the wide spectrum of users. And maybe this is also something to add in your future recommendations, also to focus on actually on uncertainty estimates in the data sets that are already there for CIs.
Yes, thanks a lot for the suggestion.
It's have been mentioned also in the ice chart working groups in several of the occasions.
Yes, I think Jonja was next, and then Craig.
Yeah, thanks, Anton. I may have missed it, but for the sea ice drift, are you not considering the possible exploration of the Doppler shift?
Yes, we are, and that was here. I was maybe I was mentioning a harmony somewhere here. Yeah, I had it on some slides. So the challenge with the ice drift is that it is too slow. So the signal is really at the level of the noise in their return signal, in their Doppler shift signal. So we need to come up with requirements that are, putting a higher threshold, actually.
But when you say that it's too low, what kind of threshold do you have in mind, or what kind of sea ice drift are you thinking of?
Well, when I was showing these results, is that it shows that with the drift fields that we typically have in the model, and which is comparable to the observations, we can hardly detect the gradients in ice drift. So for at least for LKF detection, for LKF detection is usable, but for model calibration is challenging. But it can be used, for example, for marginal ice zone detection, and of course it would be desirable to use Doppler shift for these applications.
Yeah, I think you could emphasize that in the marginal ice zone, the ice drift speeds up. And I think it would also be meaningful to not just refer to the future of harmony, but it's already there with Sentinel-1.
Yes, yeah, I agree. Yes, I was suggesting to use harmony data, but I agree it's more generally Doppler shift data from Sentinel-1 next gen as well.
Anton, nice talk. While it's a SAR conference and we're looking at synthetic aperture radar, what we have to think about when it comes to sea ice is what we really need, which is temporal revisit at a high spatial resolution. I mean, basically we've got with sea ice drift and many parameters, we've got an on-off switch. Is there sea ice or is there no sea ice? Then where does it move? And you've got the Copernicus imaging microwave radiometer, which is going to give you 8 passes per day with a swath of 1900 kilometers at a 4 kilometer resolution real aperture from a microwave imager, which is unprecedented. Plus you've got C-band at 15 kilometers. Why am I saying this at a conference about synthetic aperture radar? Well, 2 things. The first thing is that the fidelity comes from SAR. In principle, you have much, much higher resolution. You have different challenges, you have different problems, alluding to the question about uncertainties previously. But the combination of the two will give you really an unprecedented capability to get to the sea ice, to get to the sea ice drift, in a way that will revolutionize the way that we actually see sea ice. So I think that's something that we need to put into the outlook and recommendations here, that when we say synergy, we're talking about synergy with relevant sensors that will bring a game-changing capability where we can fully exploit the SAR. And we still need to develop the techniques that will allow us to merge and use the synthetic aperture radar together with the microwave radiometer. But that combo is going to make a big change. And if you even think about going further and put the altimeter on top as well for thickness, you have something that is really quite, astounding. But that's not really reflected here in the outlook and recommendations. And I think it's important.
Yeah, I agree, and I think it fits into this high resolution and long-term ice drift dataset, Lagrangian ice drift dataset, because one of the ways to merge SAR and passive microwave-based drift is to continue the trajectories when they are interrupted by absence of data or low quality of SAR data. So that's the way. And then if we have this Lagrangian ice motion over several years, that can be a breakthrough. Any more questions? Ben, one more, please.
I would say that speaking of synergy is to combine a SAR deformation with ISAT, cryosat related sea ice thickness estimations, because the SAR gives you the short-term deformation, which then you can use, and openings and closings, basically to use to verify the thickness distribution and the contribution of deformation to thickness and volume change, which is derived from the altimetric products, basically. So if you put those two together, I think you'd really have a great product for understanding everythh related to thickness, basically.
Yes, that's a very good suggestion. And in fact, in the next presentation, I will touch upon how to combine a single SAR and ice drift for better ice type classification, or namely detection of ridges. But also ice thickness distribution, it's a very valuable parameter, I agree. Okay, let me maybe continue with ice type. And as you can see, there were also many contributions for this topic, also some from other conferences and other unpublished presentations. I will again have the same structure of the presentation. So the key objectives in the presentations I have received are the following. The algorithms for sea ice type shall be robust, shall be high resolution, and also operating in all seasons. And these algorithms, like previously, they mostly work with the GRD imagery. And again, these algorithms are more about image processing or machine learning rather than signal processing and understanding of signal formation. So there is a need, or authors put objectives to derive a lot of different information from SAR. Ice extent and ice water, that's kind of classic. Then we're coming to ice types, multi-year ice, first-year ice, young ice, open water, rough ice. And then authors also want to derive uncertainties and to provide this on either level 2 or level 3. Some derive sea ice concentration and not just ice water discriminating. And in addition to stage of development, flow size is also being attempted to be retrieved from SAR. Then authors have a goal to include more data on input. This is SeaSAR temperature, multi-temporal observations, And I'm not covering here multi-frequency observations because Malin will talk more about that. And then passive microwave and wind speed and CIS deformation, it all goes to the input. And then to validate the algorithms, the authors are using visual inspection, coastal observers, icebreakers, and ice charts. And the ice charts also need cross-validation because each ice expert has his own opinion, and then ice charts never comparable. And then this is also kind of elephant in the room that no one is using texture features anymore, or no one is using good old random forest. Everyone has switched to deep learning and convolutional neural network, and particularly UNet. And I will give more results, more details about that. And then for applications of the algorithms, it's again operational monitoring, support of ship navigation directly, to combine with the drift forecast for predicting optimal ship routes, to support ice services that draw ice charts, and eventually to assimilate into the models. Now I'll go fast through innovations. And in fact, it's a pity that we cannot go deep into details, but since we have so many contributions, I had to kind of jump from one result to another. But yeah, it's still interesting. One interesting result here presented by Tura and Andreas is that there has been a large archive of collocated SAR and ice charts and AMSAR2 images. So a huge training data set was created covering a region around Greenland. And this algorithm or this data set was used to train a convolutional neural network to derive both sea ice concentration, stage of development, and the flow size. This algorithm or this data set is in fact publicly available, and it was even used for a challenge, online challenge, so that anyone could come and download the training data set and test their algorithm against the unknown data and submit the results. And there was a leaderboard where everyone could see who is the winner, and it's actually Nicholas who is in charge of this project, and it is ending soon, and there will be some publications on that. And in this algorithm, or in this work, they have developed a CNN that can classify the input SAR image and derive concentration, CIS concentration. And here you can see the ice chart that was used for training, and then the output CIS concentration. And also they derive uncertainty, which is quite important. And they also can classify different ice types or stage of development. And this is the comparison of the ice chart from an ice service and the automatic ice chart. And then they were looking at how the CIS concentration compares to the ice chart, and also what is the reliability and the uncertainty estimate of the CNN. And then they had to adjust uncertainty because it was a little bit overestimated. And in fact, this UNet is quite a standard approach now. So most of the authors in the other presentations are using this UNet for CIS classification. Another example of ice water classification is by Wang and co-authors from UIT. And a difference is that in addition to SAR, they were using also sea surface temperature. And here they show that using extra input parameter helps to improve ice water classification. And there are some examples where it is obvious. So the advanced network works better. And as you can see from comparison with the SAR images. Another example, again from NOAA, from Sean, is that they use RadarSat-2 alone for classification, and their network also gives probability of ice detection, which can be interpreted as concentration, or which can also be interpreted as uncertainty. Another example from Anja Frost and colleagues is on classification of different ice types. They were using an adjusted UNet and deriving 6 ice type: multi-year ice, first-year ice, young ice, open water, calm and rough, and rough ice. And here is a average ice multi-year ice concentration from 34 images, and it looks very realistic. But it's interesting that in addition to classifying each image individually, the authors attempted a nice approach of multi-temporal classification. So they take one SAR image and another SAR image, and there is an obvious ice drift, which they can derive. And then they use this ice drift for aligning the image, and they classify each individual image. And most of the images show that there was multi-year ice, and there was only one outlier that has shown that there is young ice. So to improve this outlier detection and the more robust classification, the authors have created, just one outlier. So the authors have created the algorithm that tracks several images and then collects the data from several images and provides a more robust classification. So of course, a high precision ice drift should be derived from these images. And then that's the result of the classification, and it shows that there was mostly multi-year ice with a few patches of younger ice categories. Yes, the challenge is that much more data is needed to calibrate such a neural network. One more research was aiming at evaluating informativeness of SAR image texture, how much we can actually derive from that. And for testing this informativeness, we took the ASIP version 2 dataset, and here is the histogram of all combinations of stage of development and flow size distribution that is present in this ASIP version 2. And you can see that some of the combinations are undersampled, so we cannot use them, or they are underrepresented and cannot be used for training the neural network. But some are well sampled, so this can be used. So already from the data set, we can see that we cannot derive all combinations of stage of development and the form of ice. And then we were training a neural network to derive the combinations that are well presented here. And we can see that for some of the combinations, like all year ice and multi-year ice, large and vast flows, and for water, the classification is very good. But for some combinations, the classification is very close, and then some of the classes are mixed up. And it means that these classes cannot be distinguished on SAR image, even though we have them in ice chart. So these kind of analyses are needed to evaluate how much we can derive from SAR data. Another example of ice classification is when we use not only texture, but also ice drift, or namely deformation. And here we can see an SAR image of a ridge and also an open lead. And this lead is not visible on corresponding VIIRS image. And this lead, And when we detect with using only textures, then some of the pixels are attributed to be a ridge on the SAR image. However, when we compute drift and when we use that to compute divergence and shear, and when we use this information in combination with the textures, then it allows to eliminate this false ridge detection. So combination of texture features and deformation improves classification and detection of ridged ice. And this is an example of application of ice classification prepared by Alexander Komarov from Canada. They were not only detecting ice and water on RCM imagery, but they were assimilating that into the model. And this is the result of the analysis of the model and the RCM data. And it shows quite good comparison with visual observations, unlike if the ice charts were assimilated. So the challenges are the following. The ice is very diverse, and some categories are not sufficiently represented in the training data. So it can be challenging to train the neural network to robustly detect it. There are some inconsistencies for multi-temporal images, how to deal with that, how to use the probability theory to correctly assess the probability of each ice category in the result. Then machine learning is in fact a black box. It's just an empirical algorithm. What can we learn from these deep learning models? And what is the physical relation between input features? And what is the theoretical informativeness of SAR image? So how much we can actually derive? And also how to improve classification in case of strong winds that look like sea ice, or new or young ice that can look as slick, and how to improve the quality of label data, because the ice charts that everyone is using now have their inherent bias. The outlook here is to use even more data on input, wind speed, solar radiation, optical, passive microwave, different radar satellites, high-resolution SST altimetry for detecting ridges, and of course, multi-frequency and multi-polarization data, and sea ice deformation. It is also recommended to provide more output variables, probability to belong to an ice category, or uncertainty in a way, to derive deformation, ridges, and leads. And I would call also ice thickness distribution here. That can be also used for assessing aerodynamic roughness that is needed for the models. And then one of the recommendations is not to mimic ice charts completely, but to create a fit-for-purpose products. So it can be either for ice services to help them classify the images, or something that can be assimilated into the models. And this is that should be different. And then it's recommended to improve training and validation data. So we need to use satellite and in situ data which are coincident with SAR. So we need to plan our in situ campaigns better. We can use data from altimeters on ridges and leads that don't have the bias from the ice charts. We need a solid training data set. That was a recommendation from one of the presentations. And then I immediately thought, but we already have one, so that should be used. And also the ice charts should be evaluated with the potential cross calibration of the ice experts. And for the applications, the recommendations are to integrate the products into ice services as much as possible, because so far there are many algorithms, but not many applications of these algorithms, and that should be improved. it is recommended to use the forecast of ice type and ship route and combine that so that the ship route can be planned better in automatic way. And then another recommendation is to forecast SAR imagery, because still, despite all machine learning and AI, the captains on the bridge or the pilots, they are still looking on SAR image or on their radar, and they trust that more than even a very nice, beautiful ice chart. So what we can do is we can take a SAR image and combine it with a very good ice drift forecast, and then provide a seamless SAR image for a given time. But of course, we need to create this SAR image very accurately, accounting for divergence and convergence, so that it's not just a smooth image, but it is realistic. And for that, we need a good forward model that can predict backscatter, ice backscatter. And then the products should be assimilated into models for operational purposes and for reanalysis for climate research. And for simulation, it's good to evaluate the impact of a simulation of different products. For concentration, it's okay. We can improve ice age. But how does a simulation of stage of development improves the model? That's not clear. And then to characterize uncertainty of these products better, because that's the value used by the simulators. And then from machine learning to human learning, we have to interpret these results of the black box CNNs to understand better the relation between input features and the informativeness. And eventually, we need a better model for sea ice backscatter so that we can simulate SAR, because we already have quite good ice models, and with inversion technique, we can probably do better than a simple machine learning. Thank you for your attention. Any questions for ice type? Eero?
Yeah, thank you. I would like to emphasize the fact about ice charts as training material. They have issues, and which we all know of. One of them is that, especially in remote areas, ice analysts like to just label them, here be dragons. So if you look at the Central Arctic, you will have very, very heavy ice, even if when you compare that against Cryosat 2, it's not. And that's natural. There are no users there. Why should they care? On that line, as you already mentioned there, if you want to have a consistent training set or validation set, look for the most recent altimetry products, ISA2, ridge detection, for example, and the Cryosat2 cryotempo products. They're beginning to be really good, and they are consistent. They do not have a human drawing them.
So do you mean that detected ridges can be used to characterize ice, like a stage of development of ice?
Oh, yeah. Yep.
Yeah, because it's definitely useful to derive roughness per se, like aerodynamic roughness, because that's what the models need. I basically don't care if it is a multi-arise 5-year-old or 3-year-old. What I want to derive is how many sails there are per.
Yeah, that's it. And the ice analysts look at synthetic aperture radar data, which is basically surface roughness, and that's where they pull their classification.
It's a different scale. But yeah. Yes. Thanks for your suggestion. I totally agree.
Thank you, Anton, for your nice talk. So, are you in touch with people working on NWP coupling models? So with the ice model, we know that it's really important to have this roughness, or what you call it, drag coefficient on the sea ice. It's I think if you have kind of product provided from from SAR measurement, it will be really useful for such coupling model in NWP perspective, I think.
You mean for not for the ice model, but for the weather model, right?
Yes, it's a couple. So.
A couple, yeah,
Yeah.
okay. Yeah. Yes, thank you very much, and I totally agree that it's there are some products from altimetry already, but it's scarce. It's a long track, and if we can use SAR data to extrapolate in space and to make it more dense, that would be only better for the models. Yeah.
Yeah, I just wanted to comment a little bit on the terminology, because across your presentation, you have mentioned when it comes to the roughness, you have mentioned ridges and then some deformation fields. And then there are also rubble fields and ice rubble and hummocks following the WMO regulations or defined terminology. And what, for example, when you're talking about applications, when you're talking about the master mariners, they operate also with a different terminology. And when we're looking at the different scales from the different satellite resolutions down to the pixel, like what we're talking about, 40 meters by 40, some of them 5 by 5, it's a optical, or even 3 meters. Then we're talking about also different features we could see on those products. And then I think it's important that maybe we will use some time during this breakout session to talk about also different terminology in terms of the different applications and scales. Yeah.
Yes, I agree. Terminology is important. Okay, Malin, please, the floor is yours.
Right. It works. Yeah, so we have the other two topics left. So in the CI's theme, so multi-sensor synergy, and these were the contributing abstracts. So we are not really covering passive microwave, we're not covering radiometry, and we're not covering altimetry. We are SeaSAR here. So this is there's a lot of focus on SAR and also some on optical images here. Oops. So I'm following the same outline as Anton has been already. So the key objectives, and this is then largely taken from the abstract that was submitted to the CI session. But I mean, some of them are obviously larger scale as well. But we want to develop new fused. There's different terminologies here used, but new and fused were mentioned in these abstracts. Combinations of methods or frequencies. And here we're talking about SAR frequencies. There were also abstracts combining optical and SAR images, so actually using then the Sentinel missions, I shouldn't say one there, but for improving CI's classification, investigation into the benefits of using multi-frequency SAR images to improve our CI's type separation. So again, we're dealing with different terminology. We've heard about CI's classifications, we have talked about CI's concentration, CI's types, and here we also talk about separating different ice types. The use of polarimetric features to separate different ice types. And also multi-frequency. And here I added X. We did not receive an abstract about X-band, but the combination of X, C, and L. We can also then talk about Ka, Ku band images. To improve CI's type classification and also iceberg detection. So when it comes to the algorithms, then we want to improve the ice type and ice water separations. There's also the testing of the applicability of future missions. So ALOS 4, which is going to have a ScanSAR with 700 kilometer swath width. So then we're getting closer to some of the other the passive microwave sensors with the area covered. And obviously also NISAR and ROSEL. And the reason for these images, of course, of the products is to improve ship safety and reduce travel time. So the results from the abstract here, the first one is from Ville et al. Where they used this huge optical or SLSTR image from Sentinel-3, combined with this, in this instance here, a quite small Sentinel-1 image to improve the ice-water separation. So they found with the SAR image alone, and then adding the optical image, you can actually have a better separation between the ice and water. And they had 6 different classes, so multi-year ice, first-year ice, young ice, and then 2 different types of open water, and then rough ice. So, yeah, to address then the open water separation from sea ice challenge in SAR images, the optical images were added. And as you can see, this fused classification then had a much better ice chart or ice type image afterwards when we added the optical images. I mean, on a day like today, we have outside beautiful blue sky and a lot of sunshine. Obviously, the optical images can be very, very useful. At other times, we have around the Norwegian coastline, we have an 80% year-round cloud cover. So optical images would then obviously have some limitations then. There is also the work here by combining C and L band. So like to look into how can the combination of the 2 improve sea ice type separation. This is also important from the ice charting services. They are very willing to incorporate L band, provided that the images will be readily provided, they will be free, and they will not be, little snapshots in time in locations here and there, but there is a consistency. So here on the left, we see a C band and an L band, and even if you know nothing about SAR, you can look at those images and you can say they look slightly different. So they do contribute different information. And here first we have a classification where we just use the C band, and then the middle here, L band, and then we have the combination of the 2. So L band or a combination of the 2 actually produces the best sea ice type separation results. And in particularly, when we're talking about the young ice and open water, then we actually need the combination of the 2 to accurately represent what we're seeing in the images. And this was tested with increased sensitivity. So we are separating into different clusters. So here's the top here, there's about 2 clusters we have the C band and we have the L band. And with increased sensitivity, then we're deriving more clusters. And what was tested here is that if you have a C band only, how much more clusters or how much clearly separated clusters can you achieve with using a combination of C and L compared to just using C band? And as you can see here at the bottom, there is quite a lot of added information by combining the 2. If you use the L band and compare it with the combination, you often add a little bit of information, but you don't add as much more information by combining them when you have the L band to start with. So the conclusion in this work here was that L band is always better at detecting the deformed ice than C band, but the combination is often equally good or better. The young ice and leads, I mean, one of the nemesis of sea ice classification for a long time. Sometimes C band is better, sometimes L band is better, but the combination of the 2 is always the best. And L band has a slightly better separation of level and deformed ice during melt onset. So now we're starting getting into that seasonality effect as well. And we can also say there will be a lot more, the longer presentations, the slightly more slides will be given in the breakout session. So then you can ask the authors if we have misrepresented anything they're saying as well. But there has also been campaigns where we had fully polarimetric data where we can then start using slightly different polarimetric features, such as the polarization difference. And this one here has tried to address one of those, the nemesis, the young ice or the new ice. And the polarization difference, it changes quite a lot depending on the ice thickness or the ice type, where it's quite different between the open water and the young ice. So we go from having very high values to very low values. And then for the deformed ice, we have a large variability. So these are images here taken from the Mosaic campaign in 2019-2020 with the C-band images and the L-band images. And actually here we have a much larger variability in the L-band compared to the in the C-band compared to the L-band, likely due to the difference in penetration depth. And because the Mosaic campaign lasted for a year and they drifted with the same, or they drifted with 2 different flows, but this data here is only from the first flow, we could see that the standard deviation of the variabilities data for both young ice, level ice, and deformed ice is much larger in the C-band data than in the L-band data. The L-band data is in the squares, but there is quite large differences that start appearing when the temperature is increasing. So this line here indicates where the temperatures turned positive. And from using all of that data, there's hundreds of images, we could see that actually for the young ice, it provides a consistent separation from the other ice types. But they have slightly different dependencies if you're using the C and the L-band frequency. The reason for using the polarization difference is that it's a reduced sensitivity to the incidence angle variation. It's got a reduced sensitivity to noise. It's using the copole channel. So we're getting away from the problem when the MEL season start, when the HV channel can quite often be challenging. And looking at the future or current, we also have RCM offers this HH plus VV mode. So it's possible to derive this one actually also using SeaSAR images. And the copole channels are also been found in a lot of previous studies to be preferable for the melt season if you want to study the melt ponds. And the results have also been found to be transferable to the NICE 2015 campaign and also on the SIRFA cruise in 2022 to Belika Bank, which I come back to a lot in the more in the in situ part of this presentation. And it was also seen here that L-band has a lot of smaller pixel spacing. The images we have from ALOS-2, the pixel spacing is half of that one from RADARSAT-2. So, and this can probably aid in the sea ice deformation extraction. So the challenges and knowledge gaps. Well, sure, more images is always better. It requires a lot more data processing power. And if we have more images, we have a better coverage both temporally and spatially. But if you want to start comparing them, they are often having several hours time delay in between acquisitions. ALOS-2, for example, is not at all on schedule with the C-band images. It's quite a few hours in between. And this kind of separation becomes challenging to deal with when you're dealing with a marine environment. And also if you're based here on Svalbard, you're dealing with the Fram Strait, the ice drifts there, even though they might be small for the Doppler shift. They are very large if you're actually going to try and align 2 images. So the data alignment can produce good results, and that was seen when Anton presented also here. But the multi-sensor data temporal gaps is challenging. Combining SAR and optical data is advantageous when it's possible, but we also have to face the fact that we're dealing with a lot of cloud, fog, and darkness in the Arctic and the Antarctic. So how can we overcome these time separations? That's one of the challenges that we're still faced with. The melt season, the use of the 2 copole channels is preferable if we want to have the data for as long as possible, not to be too contaminated by the water content. And that is possible from RCM or from other compact pole missions. So yeah, so for knowledge guys, how can we actually best assimilate different sensors and how can we best benefit from their strength? This is not a challenge to point towards the weaknesses of each of the sensors. It's actually trying to how can we use the best of what we have. So for example, the infrared is very good if you want to separate thin versus thick ice. We can get heat fluxes from that. But how can we incorporate together with SAR images? The optical images, when we have a favorable illumination, we can separate open water from the sea ice very accurately. And for the SAR, it penetrates the snow. And I put a question mark here because does it really? Are we having changes in the Arctic now with more rain on snow events and these things? When we are saying that the SAR penetrates in snow in winter, is that actually still true? But the SAR can see ice structures underneath. And just because, you know, it's always nice to look at some SAR images. So here we have an L and a C-band SAR image. Taken pretty close in time, the Belika Bank during the melt season. You can see here that there's quite a large differences between the 2 images. So yeah, time separation between different SAR sensors. From a CIS perspective, I would argue, together with some others, that a tandem mission for ROSL for automatic CIS type classification would be ideal. There's also mentioned among the abstract that looking at the mixed microsatellites, Capella space might be an option. Then we have quite short time separation. How can we utilize that? The RCM mode, the HHVV, is not regularly used, but could that be an option to point towards using this in the summer months? And to go back to what Anton was already presenting, combine CIS deformation and thermodynamics for CIS classification. We have the operational L-band SAR constellations coming up. How can we make the most out of the L-band missions that we're having, and how can we look at this into the future? And think about integrated system. We go satellite observations, assimilations, and models. And yeah, but all of these things would also need some collaboration between the different sensor acquisitions and the different satellite providers. Oops. So comments or questions on the multi-sensor? Yep. So you up?
Okay, I have one. You did not mention altimeters here.
No.
So I think you should include radar altimeter at least. We actually had one publication with ERA and some others on estimating ice thickness, combining SAR and radar altimeter. And well, it was using the traditional methods, but the next one will be using machine learning, of course.
Yep.
Thanks for the presentation. I have a question, just a curiosity on the level of understanding on electromagnetic modeling of sea ice, because you want to do forward modeling. How is, I mean, is it very mature? I don't know, I'm asking a question. Do you have multi-frequency forward modeling, coherent, to be, because you use the for example, you were talking about if you penetrate at C-band, I guess, the snow.
Yeah.
So this, I mean, models can tell you if you will or not, depending on your permittivity and everything. So I just wondering what is the status of this field, if there is a community or
With the modeling,
okay.
Not so much, no.
Okay, thanks.
Right? Yeah.
Yeah.
An altimeter question.
No, I'm not gonna say the A word, but you mentioned rain on sea ice, rain on snow events, and I was wondering what would be a feasible way to spot those, and a time series. I would, well, if you could make that to go back to 1993, that would be great. But any time series would do, or even what should we do with the Copernicus expansion missions to get one?
Yeah. Oh, yeah. No, I mean we have gone back a little bit to ERS-1, but you know the time series are very sparse. We also see not just the rain on snow events, we also see the increasing wind, strong wind speeds that creates layers, quite thick, sometimes compacted layers, which is adding to that complexity. But yeah, for the future time series, yes. And
good. We should talk.
Yeah.
So thanks. So you, fortunately, Sentinel-1 and Roselle will fly the same orbit. However, there's a discussion which you are probably aware whether they should be, how they should be spaced
Yes.
in the orbit. And of course, they can fly very close together. So you have a very short temporal separation between the L and the C band.
Yep.
Or you can have more frequent observations, but not at the same time L and C.
Yeah.
So what is your preference?
I would like to have them in tandem.
So a tandem
Yeah.
is not a tandem mission of 2 Roselle satellites, but a tandem with Sentinel-1.
I know Johannes wants to comment on this. You just send it back.
Yeah, so when you speak with the ICE services, so this is very much from an operational ICE charging perspective, they pretty much all prefer a tandem mission for Roselle and Sentinel-1. I think they were talking about maybe down to 30 seconds, but probably rather 60. Yeah, such that you can really do a multi-frequency classification there. Because the studies that we've done for that really show that's beneficial for ICE types. And I mean, we have worked in some of the things that Martin presented, and Anton showed the alignment earlier, that the alignment of data that are separated in time by several hours, it works fairly well, but it produces artifacts that make it difficult to process this fully automatically. So from an operational ICE service perspective, we want them as close together as possible. But of course, there are other people or other applications that would prefer a better, more temporal coverage. Yeah.
There is one question from the chat from Christina. Can you see any benefits of higher frequencies or images for CIs, for example, Q band or Ka band?
Yeah, I mean, that will add information about the snow. So it will definitely be good. But yeah, we need those increased computer powers that Anton talked about earlier if we're going to add even more.
Maybe just to finish the tandem.
Yeah.
So if this is a consensus here, I think even so Roselle is going to fly only in a few years from now. I think that should be then a strong push of the community here, because otherwise you're not going to get it.
Yes. Yeah. Yeah, so you see the wish list to ESA is long. You should fly everything in tandem so that we get good overlaps. Right, so I'm going to move on to ensure that no one misses neither the lunch nor the visit to SeaSAR. So the in situ data to support sea ice retrieval. And here we had some contributing work. I will focus a little bit on the contributing work and then branch out in directions from that as well. Well, the key objectives for an in situ data campaign is, and I'm going to start off a little bit controversial, as said, is never ever to validate satellite images. Many of the situ data campaigns we have are not targeting satellite acquisitions. Whereas we would wish, of course, I hope everyone in the room here, that they would. But the idea is that the in situ data should aid development and validation of new sea ice algorithms. But for this, I would argue that we need dedicated remote sensing validation campaigns where we actually target what these satellite images, what we need to validate. Where are the uncertainties? We talked about uncertainties before. There's no point in collecting a lot of in situ information of things that we already know, of things that we have established quite well, where the uncertainties lie. But we need temporal and spatial overlap. Having a satellite image taken one day and having an in situ data measurement 4 days later in an area we have sea ice drift. How are we going to combine these two things? Well, we need to do the alignment. And then we are back to, oh, did we actually manage to come back to the right location? For this, in the contribution here, we also had some instantaneous sea ice drift validation. This connects to the Harmony mission. There was also deployment of drifters. I mean, drifters has been deployed for a long time. But yeah, the deployment of drifters on sea ice and icebergs. And in the contribution work here, we also had tomographic radar measurements. But we also need to build multi-scale digital methods and systems that integrate remote sensing in numerical methods and in situ data to think about the large-scale pictures. And this to improve a better understanding of long-term variations and also improve design and operations of offshore wind infrastructure. So, and apologize deeply to everyone who's now feeling very offended that I didn't put a logo for any of your campaigns up here. We're in Norway, so there's a slightly overrepresentation of Norwegian campaigns here. We had N-Ice that drifted with the sea ice back in 2015, followed by Mosaic, who drifted for a full year in the Arctic. Here you see one of the flows, flow 1. But we also have the iceberg campaigns done by Avi twice a year, the summer and the winter validation. Nansen Legacy, a huge Norwegian multi-year project that collects in situ data. But we also have research facilities such as the Sea Ice Environmental Research Facility by University of Manitoba. So all of these campaigns, they help us collect validation data for our satellite images. Some of them more targeting the satellite validation than others. And of course, we need these campaigns. But the contributions we have here are focusing on, 2 of them are focusing on one campaign that happened last year. About a year ago, we were here in Svalbard preparing to depart, and the weather was not quite what we had it now. It was very windy and snowy and not so nice, but went to the Balika Bank area and deployed 20 drifters, starting in the marginal ice zone and moving in towards the fast ice area. So we're actually getting a gradient in the sea ice drift speeds. And then once they've fallen into the water, so we have both the ice drift and then the ocean current observations. You can see many of them went all the way down past southern tip of Greenland, and one of them ended up in Iceland, and it's going to be redeployed next week. It's come back. And these also provide wave spectra, so we can actually look at how is the wave spectra in the across the sea ice region. And they cover the transition from the freezing conditions to the melt onset. And hopefully you can see here we have a drone. And underneath it hangs one of our drifters. So we use drones to deploy the drifters also on icebergs, which I'm not sure how much that has been done before, simply because you don't really want to climb up on an iceberg and have it roll on top of you. But very nicely flown by the drone pilots at Norse. And why did we want to do this also? Well, we wanted those time series that we talked about. If you're having a drifting sea ice, having the drifters deployed on them, you can actually track the same ice flow for a longer time period. So here is the result from one of those drifters, where you can see we have nice, stable radar backscatter in the freezing conditions. And then as soon as the melt onset starts, of course, everything drops. But we know that we are following the same ice flow, and we know which region it's in, and we know how much snow there was on, we know how thick the ice is, and all of these things. And the using of drones, we could then deploy drifters away from the ship. We can get a larger spread. You can start having a network. And a large number of drifters also enable a study of temporal evolution, and the incident expected maybe is getting a bit more challenging. And the reason for this campaign was also to provide a Sentinel-1 image, and then the subsequent classification that was done on the fly via the ice service at the Met Office in Norway. And this is what it looked like out of the window from this little star here. So you can see it's pretty deformed ice, and happily for us, the classification also says that the sea ice is quite deformed in this area. It was used virtual takeoff and landing, VTOL drones, so that you can actually have them take off from the ship. You don't have to put your ship next to an ice floe, put everything on the floe, and then take off. But here they could actually take off straight from the ship. And they can fly for several kilometers away and provide optical mapping on the sea ice and also infrared information. Here it was, because this was a satellite image validation campaign, we ensured that the drones were flying in at the same time and place as we had the satellite image acquisitions. And then, yeah, here is some data collected for instantaneous sea ice drift estimates towards the Harmony mission. Yeah, the snow. There was therefore done a lot of multi-scale snow measurements. We have this snow radar drone. They went flying around away from the ship. Was also done more high resolution snow measurements to confirm that what the drone was observing was what we would be observing ourselves, which includes snow pits, snow hardness, snow depth information. And the snow information is also needed for this high resolution ground-based radar signatures that's also being compared with satellite data. So we're discriminating sources of scattering within the layered medium that the snow and ice make up, and testing assumptions associated with radar response of sea ice at C-band. So that was that campaign. There's also another contribution from Kim et al., which is using AI-based segmentation of optical images taken from the ship to retrieve ice parameters. So you can see here to retrieve information about icebergs, deformed ice, and level ice. And here we have one image taken from a ship and the resulting predicted information about the different ice types. This information was then tested during the Go North cruise in 2022. You can see that the human ice expert, when it comes to the ice concentration, is slightly better than the AI observer, but still the AI observer is a lot better than the common citizen scientist that you will find that will try and classify the ice concentration. When we're looking at challenges and knowledge gaps for in situ data collection, for the drifting sea ice, the temporal overlap between satellite images and in situ data is very important. The time separation without in situ drift makes validation of training data really challenging. It makes it also really challenging to derive good training and validation data to use in machine learning methods, because we need to align the data first. But there has been drift station, I mean, starting off with the Russian drift stations back in the 60s and 70s, possibly earlier, but also NICE and Mosaic and others who have drifted with the ice, and then we have really good drift information, of course. Yeah, it's two sets of images. We have an 8-hour time separation between these two, and you can see they're geo-referenced, but things have rotated quite a bit in that time period. Here you have 5-hour time separation, and here the drift hasn't been that strong, and now you can start then comparing the L and the C-band information. Melting in summer and sea ice drift year-round, we have rapid surface changes. So if you have a C-band image in the morning and you have an L-band image after lunchtime, during melting season, this becomes extra challenging to try and align them because you're starting having melting. So I should mention the JAXA-ESA LC project. There has been, they provide a lot of high temporal coverage during in situ data campaigns, so you can actually get a lot more data than you would do normally. But by having this information, you can do quite a lot with it. If we want to go upscale or downscale, depending on, I don't necessarily like the words because definitions, what people mean with these things, but different modes in the satellite images, fine and coarse resolution can help this. If we're having a C-band of different types, how can we go from in situ to drones to airborne to satellites to models? Like what kind of scales are we talking about? Which kind of coverage do we need? And normally we need a large spatial coverage over a site to help mitigate issues with overlapping drifting in situ data. So outlook and recommendations targeted in situ data collection, where we're actually trying to validate satellite images. It doesn't really matter which type of satellite images. It can be the A-word, the altimeters, it can be SAR, but targeted, and also targeted to solve a scientific question. Like maybe plan a little bit more, what do we need for this specific scientific question we are addressing? Over permanent stations, get the satellite data providers to provide a repeat satellite image coverage over these areas. Connect ground radar observations with drones, with SAR and other satellite images for upscaling, and consider then overlaps in time and space. Drones are a fantastic, reasonably new tool that we're having. They increase use of geo-referenced drone images. The georeferencing here is key. The ice is drifting. We needed to have it so that we can align them. Plan drone flights to relate to the scientific and operational questions. The drones have long distance capabilities, and they can collect optical images below the cloud cover. So they can actually be the link to the optical data, because we don't have the time separation between optical and SAR. They can fly whenever the SAR is flying. And we need to understand the role of snow better. So yeah, how is the snow morphism affecting the radar signature? Wind compacted layers, rain on snow events, ice lenses. We saw ice lenses already in February during N-ice. We had ridges that were 1 meter thick that we couldn't actually, or above, because there was an ice lens of 3 centimeters thickness, 1 meter up in the snowpack. Those ridges were not seen because, according to the SAR, they didn't exist. How do we deal with that? Yeah, drifters. There is an underrepresentation of sea ice drift on the, first year ice or the thinner ice types. People want the drifters to survive for as long as possible, which means that we don't put it in areas where we know we are having a huge risk of them being destroyed within 3 weeks. But in order to improve the drift estimates, we might have to look at using some of them. And yeah, data arrays so we get the high resolution deformation scales. Yeah, that's it. I see questions.
Thank you very much for a nice talk. Very good. I think it's really important that you mention here now in the outlook and remaining knowledge gaps. It's something that we have to think about in terms of snow. As you know, you didn't say it, I don't think, maybe I missed it, but you know, if you have a very thin millimeter layer of ice on the top of the snow, what does the Ka, Ku, and L see? How does it work? Because here we have a big challenge. And we may just be mapping with Ka, Ku, L differences, just where we can see this thin ice layer, or where we don't have this thin ice layer. And it's something that we have to get to grips with, because it's really difficult. And it's at the very, very heart of our retrievals. So I totally agree with what you've got here. And I think in the white paper, this needs to be a little bit elaborated so that we have pointers to help do the necessary field work and research to get to grips with an answer. Otherwise, I think we're making a big mess.
Yeah, Johnny.
Yeah, it's also on the on this challenge on the snow on top of the sea ice. And I think here my question is, do we have representatives of the Crystal mission in the room? Or someone part of the Crystal mission advisory group? So, I mean, in the Crystal mission advisory group, I assume that you are seriously discussing all of this. And no, I think that there's one key thing that we need to invoke into the recommendation, and that is that ESA needs to now understand that they shall no longer do a validation campaign purely for Crystal. It shall be a validation campaign for Crystal together with all operating missions like Sentinel-1 and Rose-Al when that comes, and so on and so forth, and not at least Simmer. So this needs to be hammered in, because if we can get this to be done in a complementary way, rather than individual mission by individual mission, we may in fact win something. So ESA, we will come after you with this recommendation.
Thank you for the solid recommendation. And point taken, totally agree. Not only totally agree, but actually at the European Space Agency, we have a new program called the Sentinel User Program, SUP, which has a considerable budget. which is about making sure that we can understand how different missions work in synergy. And of course, when it comes to sea ice, one size, one mission doesn't fit all. And we have Sentinel-1, Sentinel-1NG, Sentinel-3 next generation topography, as well as Roselle. All of these missions will work in synergy with a matrix that is the SIMA microwave radiometer. And so any campaign that we do now will be almost tailored by default towards that direction. So I think the recommendation is good, and it should make its way into the text in perhaps nicer language than what you said, Johnny. But we will do that because it's obvious that needs to be done. And it's a difficult area. It's a difficult piece of work to do because getting up to the Arctic or the Antarctic into the sea ice is not easy. But unless we do this, I think we're wasting our time to a certain extent. We need to make sure that we are on top of what's going on. There is another piece of work that's taking place, which isn't reported here, which is part of the new Earth Observation Mission Ideas studies, NEOMI, which is Rosemary Willett and Julianne Strove, who you know, and they're working on a study now, which is using the KUKA radar from the Mosaic campaign, and there'll be another campaign in Churchill Bay next year to try to get to grips with this whole KA-KU band story, because it's really worrying what we're seeing. I mean, in principle, we should be able to do the job. What Yoni is saying is quite right. If we want to get the best result, we will have to combine data from different missions. And it's a question of system architecture and how we empower and engender our ground segment, which is new. So we will have a very different kind of ground segment than we've had before in Copernicus in the next few years, which in principle ought to be able to provide different data sets from different missions to solve a particular thematic area. And so I'm very interested to hear in your white paper, what combination of data would be giving you the best bang for the buck in terms of getting to sea ice? Is it a combination of SIMA, Crystal, Sentinel-1, or whatever? Put it in the paper and say, look, you should be providing these data sets in geophysical terms together as a sea ice thematic output, because that's really useful. And it's potentially, I'm not guaranteeing, but it's potentially something that could be done in the future ground segment.
And I guess everyone is eager for the lunch. And we finished early. I think we deserve an applause for that.
I promised Tom that if you finish in time, he can have 3 minutes.
Does he want this one?
Yeah.
Yeah.
Want that one?
It's still on.
I did not see that coming, Tom. But this one? Yeah. You have 3 minutes.
Okay, perfect. So my name is Tom Rune Løknes. I work for Norse. The first clarification to be made, it's not the Norse hangar we're visiting. We're visiting the hangar of Lufttransport, which is a commercial airline company which operates here in Svalbard. They have 2 of these Dornier DO-228 aircraft. They are used for passenger and cargo and logistics in and around Svalbard. They fly between Longyearbyen and Ny-Ålesund, and they also fly between or to Station Nord in Greenland. So that's the easiest way to get logistics to the base on Greenland. So they fly there about 20 times per year. So one of these aircraft, Norse, we have equipped for science missions. So we're targeting like a dual use of the aircraft, both logistics, passengers, cargo, but also to be able to collect science data. And you can see under the belly of the aircraft, there's a small pod. It's not so small, which contains some equipment that we could have a look at when we get to the hangar. So you can see the strategic location of the aircraft in Longyearbyen. That is the range of the aircraft before it has to return to Longyearbyen. Of course, if you refuel somewhere else, you could significantly significantly extend this range. So the current instrumentation is mainly an optical sensor package. It's a hyperspectral imager. It's a medium format camera. We have a broadband radio, so we could do real-time relay of images. We can do onboard processing. We have an AIS repeater on board, so all ships in the area will get a significantly extended AIS coverage when the aircraft is flying. And we also have a good inertial navigation system for the georeferencing of the data. And we're also working to realize a dual frequency airborne SAR system to be permanently mounted on this aircraft. And I know there are also initiatives to mount an airborne LiDAR on the aircraft. So that's it. I hope we can go into more details when we get to the hangar or later during the week. Have a nice lunch.
Thanks, Tom. So the bus that will first go to Svalsat for the excursion there, and after that to the Lufttransport hangar at the airport will depart 13:30, so 1:30. Nothing in this country happens on time except ski competition starts and the bus to Svalsat. So just so you know. Okay, enjoy your lunch. See you in an hour.